Good afternoon, dear friends. We continue to study electrical circuits with distributed parameters. Today we will transform the basic equations of the line for the case of sinusoidal currents and voltages. In this lecture we will formulate our problem and recall the main parameters of a sinusoidal signal. Let us also recall how sinusoidal currents and voltages can be represented using complex numbers. Then, based on the system of telegraph equations, we will obtain the basic equations of the line in the sinusoidal signal mode. We will end this lecture, as always, by drawing a number of conclusions. But first, let's briefly recall what we talked about in the previous lecture. In the last lecture, we were able to construct the basic equations for a line with distributed parameters. We used for this section of the line of infinitely small length, and therefore we were able to apply the theory of circuits with lumped parameters for this small section. The basic equations relate the partial derivatives of the current and voltage in the line with respect to time and spatial coordinate. We have called these equations as telegraph equations. They were first obtained by Oliver Heaviside while studying processes in the transatlantic telegraph cable. We learned that telegraph equations are a system of partial differential equations. Analytical solutions of such equations is generally impossible. However, if the law of change of current and voltages with time is known, as for example in the sinusoidal signal mode, then the basic equations will be simpler. In this lecture, we will get the basic equations to a line in sinusoidal waveform mode. First of all, let's formulate our problem. We have a system of telegraph equations in general form. This system is shown here. As we know, the currents and voltages that enter this system are functions of two variables. The first variable is the time. The second variable is the spatial coordinate. This coordinate determines the position of the point in the line at which we need to find the current and voltage. Let us assume that the current and voltage in the line change according to the sine law. This means that we already know the law of current and voltages change in time. It is described by the equations shown here. This equation defines the law of current change with time, and this equation determines the law of voltage change. Let's remember the previous lectures. In these equations, the letters I and U in small registers denote the instantaneous values of current and voltage. But the capital letters I and U with the index M define the amplitude or maximum values of the sinusoid. Omega is the angular frequency, and the letter C with indicates I and U denotes the initial phases of current and voltage. We talk about this in detail in the topic AC electrical circuits. If the law of change of current and voltages in time is known, then from the solution of telegraph equations we only need to determine the law of change in the spatial coordinate, only in the spatial coordinate. Let's get started. In our lectures on the topic AC electrical circuits, we said that the sinusoidal functions of time can be represented as a complex number. The instantaneous value of sinusoidal current can be represented by a complex of instantaneous current value. You can see the corresponding formula here. Please note that we denote all complex quantities with a dot above the corresponding letter. The instantaneous value of a sinusoidal voltage can be displayed using the complex instantaneous voltage value, which is given by this formula. The formulas for instantaneous values of current and voltages complexes include the complex of the amplitude value of the current, the complex of the amplitude value of the voltage, and the exponent to power of g omega t, which is called the rotation multiply. As we know from previous lectures on the topic alternating electrical circuits, all equations that are valued for instantaneous values of circuits and voltages are also valued for complexes of their instantaneous values. Therefore, let's rewrite the system of telegraph equations for complexes of instantaneous values of current and voltages. This system is shown here. Pay attention to the dots above the letters U and I in these equations. This suggests that in their equations we use complex number. Look, according to the telegraph equations, we must find the partial derivatives of the complexes of instantaneous values of current and voltages with respect to the spatial coordinate and in time. In complexes of instantation values of current and voltages, we only the complex of the corresponding amplitude value depends on the spatial coordinate, and the rotation multiplier depends only on time. Thus, complexes of instantaneous values can be represented as a product of two factors. The first factor depends only on the spatial coordinate, and the second depends only on time. This fact simplifies finding partial derivatives. Indeed, finding the partial derivative of the complex of the instantaneous value of the voltage, we must write the product of the total derivative of the complex of the amplitude value by the rotation factor. The total derivatives can be used because the voltage amplitude complex depends only on the spatial coordinate and therefore is a function of only one variable. Similarly, you can write the partial derivative of complex of the instantaneous value of the current. Let's move on to finding partial derivatives with respect to time. The complexes of amplitude values of current and voltages do not depend on time and can be taken out of the sign of the derivative. Therefore, we only need to find the derivative of the rotation factor, that is the derivative of the exponent to the power of g omega t. As we know from the mathematics, this is the product of the same exponent and second multiplier is g omega t. The derivatives are found and we can substitute them to the telegraph equations. On the right side of this slide, we once again wrote the formulas what we are just obtained. Let's perform the substitution of derivatives of current and voltages in the telegraph equations. Consider the first equation of the system. On the left side of this equation, we have substituted the total derivative of the voltage with respect to the spatial coordinate multiplied by the rotation factor. The product of the complex of the instantaneous value of the current and the resistance R0 plus the product of the inductance L0 and the total derivative of the current with respect to time are substituted on the right side. Note that the rotation factor is present in all terms of this equation, so we can cut back on it. Similarly, we transform the second equation of the system. After reduction by the rotation factor, we obtain such a system. Let us designate the sum R0 plus g omega L0 as Z0 in this system, and the sum g0 plus j omega c0 as y0, and we finally can obtain some such system. This is the system of telegraph equations in the case of a sinusoidal signal in the line of distributed parameters. So we have received a system of telegraph equations for the case of a sinusoidal signal in a line. Note that this is now a system of total differential equations, and we know how to solve such systems. Please also note that this system is written for complexes of amplitude values of currents and voltages. It no longer contains a variable t, but determines the law of change in the complexes of currents and voltages depending on the spatial coordinate x, only the spatial coordinate. We can say that the variable t, time, is SSVR, hidden in complexes of amplitude value. After all, knowing these complexes, we can write down the functions of time corresponding to them. In the future, to simplify the equations, we will write them not for complexes of amplitude values for currents and voltages, but for complexes of their effective values, as it shown here. Look, in this system, there is no longer an m-index next to the complexes of currents and voltages. So, our lecture has come to an end. Let's draw some conclusions. In this lecture, we have obtained the basic equations of a line with distributed parameters in the sinusoidal signal mode. First of all, we have replaced the instantaneous values of currents and voltages with their images in the form of complex numbers. As a result, this allowed us to get rid of the variable t, time, in the resulting system of equations. This system is a system of differential equations in total derivatives. We can solve such system of equation. This means that we can solve this system and find the law of change of currents and voltages in the line in the sinusoidal signal mode. The solution of the system will be the topic of our next lecture. Thank you very much for your attention.